Hi everyone, my name is Daniela and I will talk about private stream aggregation and more concretely lattice-based private stream aggregation. I will first give an introduction into what private stream aggregation is and what kind of problems we're solving with that. We will also look into one particular PSA scheme that existed previously, and I will cover some theoretical basics around learning with errors and augmented learning with errors, which are essential to understanding our scheme, which is a lattice-based PSA scheme that we call LAPS. I will present a general construction for our scheme, but also show a concrete instantiation, including some experimental results from our implementation. Finally, I will draw a conclusion and also give an outlook onto some potential future directions. All right, so private stream aggregation itself solves the problem of having a distributed set of users that each have privacy-sensitive data that we would like to aggregate without trusting the aggregating party. So we will here look at the most basic form of aggregation, so we'll say the sum. You can also think of more complex ones like, for example, the product. But the gist of it is we don't trust the aggregator. We do think that he will honestly behave according to the protocol, so he will perform the sum, but we don't want to leak any sort of information about any individual users or their data to the aggregator. And the way PSA schemes solve this problem is essentially by combining differential privacy techniques together with encryption techniques. So what's going to happen is that each user takes their sensitive data, DI, and applies a so-called privacy mechanism, which essentially just means that they're going to add a certain noise to their data, and thereby creating a noisy version of the data, which is here denoted XI. The user will also encrypt that data and then send all of those ciphertexts to the aggregator. Let's for a second assume that the aggregator has a magic way of computing unencrypted data, and he's able to indeed aggregate those ciphertexts, so in our case, compute the sum of the ciphertext, and then only decrypt the noisy sum of the user's inputs. And the guarantee of PSA schemes is that this aggregate result does not leak any information about any of the individual users or their data. And the formal notion for PSA schemes is aggregator obliviousness, which essentially guarantees that, again, the aggregator doesn't learn anything but the noisy sum from the user's data points. So what's going to happen in practice is that we're going to implement a noisy encryption routine on the user's end, which essentially combines the deployment of the privacy mechanism together with the encryption. And the decryption routine of the aggregator, again, combines the aggregation of the input ciphertexts as well as the decryption. And another thing that's special about PSA schemes is that each of those users for their encryption routine is going to have an individual unique encryption key in order to ensure that the aggregator cannot decrypt any individual ciphertext, but only the aggregate, in our case, the sum of the ciphertexts together. So one particular PSA scheme that was introduced by Shi et al. At NDSS 2011, and it's also the first PSA scheme that was proposed, is the one that we show here. So on the left-hand side, you can see the encryption routine of the user, and on the right-hand side, you have the aggregator's decryption routine. So what happens here first is the user is going to add some noise. So in Shi et al.'s case, she samples some geometric noise and adds it to the data and creates a noisy version of the user's data, which is called XI. And then the encryption is just a discrete log style encryption where you have G to the XI, which is that noisy data, times the hash of some public value T to the power of the user's secret encryption key SKI. All of the users sent their ciphertext to the aggregator, and he's now tasked to compute the sum of those noisy data points. In order to do that, he will actually compute the product of the input ciphertext. Why is that? Because we want to have the sum of those noisy data points in the exponent. So what you see here is G to the sum of those XIs, and together multiplied with that hash value to the sum of the user's encryption keys. Now the question is, how do we get rid of that second part in the term? And here's actually where Shi et al. Deploys sort of a trick in that they define the aggregator's decryption capability, so the aggregator's decryption key, as the negative sum of the user's encryption keys. Therefore, he's able to cancel out that second part in that term, and we're left with only that G to the sum of the noisy values, which we're interested in. Now, in the last step, and that's actually also the main open problem from this work, we need to solve a discrete log to get to that exponent. Of course, this significantly limits the plaintext space that we have, and therefore the size of the user inputs that we can use in this aggregation scheme. So our foremost goal was to overcome this previous limitation and therefore extend the plaintext space. But we also wanted to improve the security guarantee, because actually Shi et al.'s PSA scheme is based on a Diffie-Hellman assumption, which is known to be breakable by quantum computers. So what we did was not only resolve the open problem by extending the plaintext space, but actually also provide a post-quantum security guarantee, which means it will remain secure when we have a quantum adversary. And as it also turns out, we're able to improve efficiency with that construction in the decryption routine, which is roughly 150 times faster than in Shi et al.'s PSA scheme. And the way we can do that is by using an LWE and learning with errors-based construction, which has a certain relationship with lattices, and hence the name lattice-based PSA. All right, learning with errors. So let's imagine for a second we sample some matrix uniformly at random, A here on the left-hand side, and multiply it with some secret vector S, also sampled uniformly random, which will give us another result, which is also a vector B on the right-hand side. Now, if I ask you, given A and B, find the vector S, you're probably going to tell me that's easy, and you're right, just use Gaussian elimination. But as it turns out, if you add a little bit of error to each of those equations, this problem actually becomes quite hard. In fact, as hard as worst-case lattice problems, which are assumed to be post-quantum secure, and hence the LWE assumption as a hardness assumption is also assumed to be post-quantum secure. So a regular LWE term essentially looks like this. We take some matrix, we multiply it with that vector S, and we add some error that is sampled from a discrete Gaussian distribution. Now, augmented LWE basically looks the same, except that that error is not sampled from a discrete Gaussian, but from a distribution that looks like a discrete Gaussian, but isn't one. So what we end up with is a term that essentially looks just like an LWE term. It is indistinguishable from an LWE term, can therefore inherit all of the security properties, but we can actually use that error term as a data container. We can embed a plaintext, a message, into that term by leveraging the special way the error distribution is constructed. And this is how that works. So let's assume we have some plaintext M that we would like to embed into that error term. What we're first going to do is we're going to encode that message. Here we just assume it's some function. It has to satisfy certain requirements, but for a second, let's ignore that. So just imagine some sort of mapping of that plaintext M into some vector V. Now, this vector V, together with a so-called gadget matrix, are going to define the way this error distribution is going to look like. So we construct that error distribution, we sample our error term from it, and then we construct the rest of the term just like a regular LWE term. So what we end up with is a term that looks like LWE, is indistinguishable from LWE, and inherits all of the security properties, but actually contains this message M. So actually, you can look at that result vector B as an encryption of our plaintext M. Now, assume we have that term. How do we get that message back? So essentially, how do we decrypt? Let's assume that we know the secret key S. The matrix A is public. So first of all, what we need to do is retrieve the error term from that result vector. So what we're going to do simply is to add the negative product of that coefficient matrix A and the secret key S. So now we have the error term. And now what we're going to do is leverage kind of a special property of that error distribution, which is when you multiply the gadget matrix G with the error term, you get that encoding V of the message back. So we have our V, and now we only need to invert that function that we used in order to encode, so essentially decode to get our message M back. So we're going to use this ALWE-based encryption within our construction. Now, if you look at our PSA scheme or our construction on a high level, it looks just like any other PSA scheme. So you have your distributed set of users and their sensitive data DI. They implement some noisy encryption routine with individual encryption keys. They send their ciphertext to the aggregator, and he's indeed able to get that noisy output with all of the privacy and security guarantees. The way those ciphertexts look like is it's going to be some matrix multiplied with some secret vector S plus some error, and I hope that sounds familiar because that is our augmented LWE term that we just talked of. And what we're actually able to guarantee is not only that this aggregate output doesn't leak any information about the individual users or their data, but also that you're not able to decrypt any individual ciphertext, even if you had a quantum computer to do it. So we're able to guarantee post-quantum security. All right, so let's look at this in a little more detail. Again, on the left-hand side, we have the user's encryption routine. On the right-hand side, we have the aggregator's decryption routine. And the first thing that's going to happen, as before, the user is going to add some noise. So you can imagine, say, the geometric distribution, but it could be any sort of noise distribution, to create this noisy version of their input data. So we end up with that noisy version, xi. And now we're going to encrypt. Now, if you remember in our ALWE-based encryption, this is where I assumed, well, let's just use some function. But actually, for all of this to work, we need to make sure that this encoding is additively homomorphic. Why is that? Because we want to make sure that the aggregator, when he aggregates all of the input ciphertext and decrypts, he's going to compute the sum. So we need to make sure that the sum of those encodings corresponds to the sum of the underlying plaintexts. So the way we ensure that is simply by defining this encoding step as the encryption routine of an additively homomorphic scheme, additively homomorphic encryption scheme. Hence, it means that the sum of the ciphertext is going to correspond to the sum of the underlying plaintexts. So we're going to compute or generate this VI as essentially an inner ciphertext, if you want, and then just follow the other step of our regular ALWE-based encryption. So we're going to construct our error distribution based on this VI, together with that public gadget matrix G, sample our error term from it, and then construct an LWE-based term in the end, which is our ciphertext using the user's secret encryption key. Again, all of the users are going to provide their ciphertext to the aggregator, and he now somehow needs to compute the sum of the noisy inputs. So what he's going to do is indeed compute the sum of the ciphertext. So he's going to aggregate those inputs. And now in our ALWE-based decryption, we assumed we knew the secret key. Obviously here that's not an option because we don't want the aggregator to know the user's encryption keys. So actually what we're going to do is kind of deploy the same trick that she et al. Also used, in that we define the aggregator's decryption key, his decryption capability, as a negative sum of the user's encryption keys. So in this case, he can just compute that A times S0 that you see in the back, and therefore cancel out all of the other terms around it and retrieve the sum of the error terms alone. From here on, we do the same thing as before in ALWE-based decryption. We use this special property of the error distribution and multiply that gadget matrix with the sum of the error terms to get the sum of the encodings of the messages that we're actually interested in. Now, since we generated those encodings using the encryption routine of that additively homomorphic scheme, we're simply going to use the decryption routine to get the underlying plaintext back. So in the last step, the aggregator is going to deploy or invoke that decryption routine together with a secret key that he obviously also has, and get indeed the underlying noisy sum of the user inputs. So for correctness, we require that obviously this additively homomorphic scheme is indeed additively homomorphic and correct, and by leveraging this special property of having the product of the gadget matrix with the error term giving that encoding of the message. Now for security, as I said earlier, what we would like is post-quantum security. What does that mean? We want to show that this encryption here, breaking that is as hard as breaking worst-case lattice problems. What do we do in order to show that? We need to show that that term that we get as a ciphertext is indeed indistinguishable from an LWE term, because we know LWE is as hard as worst-case lattice problems, and it kind of gives us the rest of the chain. How do we show that? We need to show that that error distribution that we use, that we constructed here, is indistinguishable from a discrete Gaussian distribution, because that's what makes that term look like an LWE term. The way to show that is that we need to show that VI, that encoding that we use in order to construct that error distribution or that term, is indistinguishable from random. And the way we ensure that is by not only requiring that the encryption routine of this additively homomorphic scheme is semantically secure, but it also produces pseudo-random ciphertexts. Why is that? Because the output of that encryption routine is exactly going to be that VI. Hence, if that is a pseudo-random ciphertext, we're able to satisfy that requirement and get the rest of that proof of chain. So in that sense, we're able to prove security both in the semantic sense as well as the aggregator oblivious sense. Now, finally, in our instantiation, we used a discrete Laplace mechanism for the privacy mechanism, which is essentially just a discretized version of the very common Laplace mechanism from differential privacy literature. And we used a reduced version of the BGV encryption scheme for the additively homomorphic scheme. Now, the BGV encryption scheme is an LWE-based fully homomorphic encryption scheme, which means it supports both homomorphic addition as well as homomorphic multiplication. Now, of course, here for the sum, we don't need homomorphic multiplication, and therefore we reduce that scheme to only homomorphic addition. So technically, it's a somewhat homomorphic scheme now, because that also improves efficiency. Now, if we look at the results here, first of all, on the left-hand side, you see She et al.'s results. So that's the baseline for our results here. On the right-hand side are our results. The first thing you see, of course, that all of this is pretty practical. With under 4 milliseconds for encryption, under 2 milliseconds for decryption, that's pretty doable. The other thing that's notable, of course, is the extension of the plaintext space. So where previously you could only encrypt bitwise, we're able to extend that to up to 2 to the 16 as a plaintext. And another thing that's particularly noteworthy in the decryption routine, we're able to improve the runtime by roughly a factor of 150, considering that the plaintext is even larger afterwards. All right, so in summary, we proposed a novel lattice-based private stream aggregation scheme with strong security and privacy guarantees in the sense that we're able to provide post-quantum security based on the LWE-based assumption, and differential privacy comes from a deployed privacy mechanism. We're also able to achieve significant efficiency improvements, both in terms of the runtime as well as the plaintext space. Now, looking forward or into the future, an interesting thing to look at would be to allow for user failures, because currently in our scheme, we do require that all of the users indeed provide a ciphertext. As soon as we're missing one, just like in Xi et al.'s scheme, you would have to restart the protocol. So dynamic joins and leaves would allow for essentially user failures. Another thing that would be interesting would be to enhance our scheme to aggregator unforgeability. Now, aggregator obliviousness does guarantee that it doesn't leak any information from the user's data and so on, but it doesn't guarantee that the aggregator is going to publish the result that he has actually computed. Now, aggregator unforgeability gives public verifiability of the result that he's going to publish. So the aggregator actually has to provide a proof of correctness together with the aggregate output. On a high level, the way to do that with our scheme would be to combine our scheme with a homomorphic aggregate signature scheme, such that each user would provide a signature together with their ciphertext, which then the aggregator can aggregate together with the output, and therefore get an aggregator proof of correctness that he can provide when he's publishing the result. Thank you very much, and I'd be happy to take questions.
Just a quick question. How well does this scale? So let's say if you want to go to 100,000 users or 1 million users.
So in terms of number of users or participants, it scales linearly. So even if you go up to 1 million users, you're still under a second for both encryption and decryption. Yeah.
Hi, thank you for your presentation. It is very interesting. And I would like to ask you, can this be applied to online voting, for example, where you want to, aggregate the sum of all the users, the vote of the users, but you don't want to leak the single vote. You can do the first step on the client, so the browser of the user, and aggregation on the server side. Is this applicable or not?
So if I understand correctly, you're asking whether we could use PSA schemes for voting. On a high level, I would say yes. For this particular scheme, and that also applies to anything that's kind of Xi et al. Style, you do need a trusted setup. Because if you remember the way the aggregator's decryption key is set up, it's a negative sum of the user's encryption keys, and some party needs to be able to distribute those keys ahead of time that you do need to trust. So that may be a challenge in implementing it for voting, but I'm sure it would be an interesting direction to go.